this is a real easy thing to remember. And just do these kind of outlines because they put things in perspective and give you some foundation as we go forward into the more detailed stuff. MALT. That's nice. I'll give acronyms when I can figure them out. But what do measurements do? They provide meaning to the environment, the surroundings. Oh, I'm going to put environment. I like that better. Measurements answer questions. Measurements limit behavior. And function as a tool for analysis. Comparative analysis, I want to make. So, starting with this, at least you can have an appreciation of what measurements do. And it's really easy. You remember MALT pretty quick. And if you study it for 5 minutes, you should be able to answer a question on that on a quiz or something, which is about as detailed as it's going to get. Now, when we get into making a measurement, it is a descriptive device. Measurements are descriptive devices. That is, they have to give meaning, like I said up here, to whatever we're studying. That is, they give meaning to the object of interest. Length, width, height, weight, lumens, those kind of things need to be looked at with more detail. Okay, measurements being descriptive devices. When you speak to somebody, and this goes without saying, you want to make sense. Yes? So if you were going to speak to somebody about something, you would want to present your idea in a way that whoever you're talking to would understand it. Okay? And that goes without saying. Well, there are three elements to that. And it kind of forms around DSC. I went to school in Mississippi my first couple of years, Delta State University. It was called Delta State College at that time. So that's how I remember that. And D stands define and standardize and compare. This is the essence of making sense, especially in measurements. When you talk about defining a measurement, we're talking about defining the fundamental quantities. Now, actually, there's 7 fundamental quantities. There's length, weight, time, lumens, quantity mass, or just quantity. Oh, there's one other. 1, 2, 3, 4, 5. Need 2 more. Lumens, quantity. That's what I wrote my note down because I don't use much of it. Okay, there are 2 more that actually go with this we will use eventually, but I don't remember exactly what they are for the moment. But at any rate, these are the 3 that we want to define. Well, what's the length? Okay, everybody kind of understands what length is, and breadth and height and stuff like that. Do you understand what weight is? Yeah, from our perspective of in our reference frame. Yeah, we know what a weight is. Okay, throw it on a balance and we get a number. Okay, that's weight. Time, I think most people know how to use a clock. You can tell time. Okay, lumens refers to a brightness factor. Oh, sound. What is it? Decibels or sound volume. And there's there's a couple of 1, 2, 3, 4, 5, 6. There's one more. I can't remember exactly what it was. Which one? Seems like there's 7, but it'll pop up. I don't need it for short term. But length, weight, and time are the ones that we will start with. We know what time, length, weight are. So that's what the first thing in making sense in measurements are, is to, well, I don't know what we're measuring. Well, that goes without saying. Now we need a standard for each one of these. And so when we talk about standards, we want a standard of length, the quantity, weight, and of course time. That's what we've got these defined, so we need standards. Well, we know of 2 systems. Those standards are established relative to systems, and we know about the English system and the metric. And we'll leave it to the MKS system, or the SI system is what it's called. The MKS is meter kilograms second. And so the same thing as Standard International. Okay, so when we talk about standards in the English system, of course that's the foot, 1 foot. And then weight is 1 pound. And time is 1 second. And these are abbreviated, as you know. I'm telling you stuff you already know, but it still needs to be covered and put in perspective. That's more than anything. Now, over in the metric system, in the MKS, that's what it means, meters, then the kilogram, and the second, the standards are 1 meter, 1 kilogram, which is a multiple of a fundamental, and of course 1 second also is in the MKS system. So it's 1 meter, 1 kilogram, and 1 second. So we have those we already know about. Okay? Now you have standards for lumens and quantities. That's the quantity of the mole concept. We'll get into that in the next chapter, or well, chapter after. Anyway, and sound, what is it called, decibels and stuff like that. But we're not going to be working with that. That's why I don't remember them, because I don't ever work with them. Anyway, so when we start out, we have to have some kind of idea of what our size relationships are. Here, of course, is the 1 meter stick. And so when we measure things, we measure objects of interest, measurements for objects of interest, maybe fractions of a meter, or many times of a meter, that describe whatever it is we're interested in. And weight, we define ourselves as having a certain weight, okay? And it relates to maybe our health conditions or whatever. And so we pair these standards with something else, and it's called a comparative analysis. And so we've got standards, and we've got the measurements defined, standardized, and now a compare measurements. That is, you're comparing whatever you're measuring to the standard, a mile. We all understand a mile. Is that bigger than the standard of length in the English system? Yeah, well, of course, foot. It takes 5,280 statute mile feet to make a mile, and you know, of the standard 1 foot. Okay, pounds. Okay, we measure, say, the weight of a bovine cow. So what's the average of a bovine cow weight, or something like that, and we measure it in pounds. Okay, and typically if we fly in an airplane going somewhere, we might be aware of the time frame. Well, on the average, it takes 2 hours to go from Atlanta to New York, I don't know, to Charlotte, North Carolina, I don't know. And so we say 2 hours. Well, how does that relate to the standard of time? Well, a whole lot of seconds, I think a lot more than 1 second. The idea is you're making measurements that ultimately compare with the standard, so you can have a meaningful understanding of what's going on around you. Without it, it just doesn't make any sense. So this is also known as a comparative analysis. So I'm just hitting some of the organizational perspective issues that we'll be needing from a fundamental standpoint as we go through this. Now, next topic is content of a measurement. Measurements consist of 3 issues: a number, a unit, and an uncertainty. An uncertainty factor is what I call it. Well, of course, we recognize that we got to have a dimensional aspect, so the number provides that dimension. But you have to have some descriptive unit that goes with that dimension, that number, to have any meaning. If I just blurted out 8, that wouldn't mean anything. But if I said 8 pounds, and everybody's on the same page. So you see what I'm talking about. Now, if we're doing scientific measurements, there will be an uncertainty factor. Now, there are measurements called absolutes, like 5 apples in a basket. There's not a whole lot of uncertainty in that. And that's called absolute quantities. But what we're talking about is when you make a measurement, you've got your detector. You're a detector, okay? And so the lady here's got a detector, and she measures the blue is a 14. Well, next lady over measures the blue as a 13.6. And then with 13.9, and then 14.2. And so we have a variation going on. And so we need to incorporate that variation into our descriptive aspect, and that's where uncertainty factors come into play. Now, in working with this number issue, both of these kind of go together because you have variations in numbers because of experimental equipment. I learned a long time ago you need to write it down so people will understand. They can see and hear and write it down. So our ladies that are detecting the color blue or our detectors, and there's a variation because of what they see. Their eyes say 14, 14.1, and whatever I said a while ago. Those are variations, okay? And they're always due to variations in the instrument's readings. Now, that didn't say the instrument was bad or the instrument was different. I said that just because of the nature of whatever's being done, the object of interest, the nature of object of interest, you're going to get variations in data. They're not all going to be the same recorded numbers. And so you have to be able to deal with that, and that's where the uncertainty factors come in. And to deal with uncertainty in numerical data, we use significant figures. Now, there are rules for significant figures. These are all digits known with certainty plus one uncertain digit. kind of splitting the difference between the lines, so to speak. I think it's halfway, or somebody else may think it's 3/4 of the way. That's what I'm talking about. I think you understand now. But in your outline, if you look at the second half of the outline that I gave you, these are the published rules in the IUPAC, International Union Pure Applied Chemistry book, for significant figures. They're great, and you need to be aware of them. But there's a better way, which I'm going to show you right now in a little video. Okay, these are multiplication, and division. Round answers to match So this layout gives us, computation gives us that as a calculator answer, which is, you can see on the calculator just about as easy as anybody else can. But round to 2 sig figs, we look at this and say, okay, the 2 sig figs would be in this particular number, since it has a big fat decimal right there, left to right count. So this would have to be 160. So that's 2 sig figs. Now, when I set the 0 in there is not a significant figure, doesn't mean it's unimportant. You have to have it in there for dimensional considerations, obviously. But for the nature of it and what we're trying to teach you, that's the idea, okay? Now, when you're working addition and subtraction, you want to round to the least number of digits to the right of the decimal. I'll say that again, round to the least number of digits to the right of the decimal. So when you look at this, you notice this particular number, 415.1, has only 1 digit to the right of the decimal as given. So your rounding should be to here. Round to that point. Okay, so your answer, your appropriate answer was 451 point. Okay, that's got to go to a 3. 6 changes. We'll use the 5 plus rule. 6 will take 4 to 5, and 5 will make 2 into a 3. So this is your appropriate answer. Rounded to the least number of positions to the right of the decimal. Okay. These exponential notations are powers of 10, and expressing numbers in powers of 10 requires a little explanation. So if you're given numbers greater than 1, then what you'll do is move the decimal to the left and apply a positive power of 10. Two, 3, 8, 0, 0, 0, 0. Okay, you assume the decimal is on this last position right here, and you can move the decimal to the left and use a power of 10. in this particular one, if that's what you want to do. For numbers greater than 1, you can put that decimal anywhere in that number you want. You can put that decimal in that place or that place, there, or there. And they all mean the same thing when you write these out. 238,000.0 times 10 to the first power, or 23800.00 times 10 squared, 238.000 times 10 cubed, and so forth. 238.0000 times 10 to the fourth, 23.81234 times 10 to the fifth, make 5 look like a 5, and 2.38000 times 10 to the sixth. This is called the coefficient number. When the coefficient is expressed between 1 and 10, not being less than 1 or at 10 or above, between 1 and 9 something, this is called the standard form. And in most data streams, when you look at problems, that's what you will be given, a standard form in that computations. But all of those are the same. And so please try to look at that if you can, and try to understand that placement of the decimal. Well, in numbers less than 1 and above 0, certainly you just do the move right and use a negative power of 10. So we have 0.000234. We want to express that in exponential notations. Again, we can put that in any of the positions as you go through this. But when the coefficient is expressed as a value between 1 and 10, or less than 10, it'll be standard form. So this number would be 0.002345 times 10 to the minus 1, 0.02345 times 10 to the minus 2, just to make a set of data for your notes. There's 3. There's 4. You can even go beyond that and go to 23.45. You don't put all the anything but the first decimal zero in there. You don't have to put these in. 23.4, so you're moving over here from here 1, 2, 3, 4, 5, so that'd be 23, 2, 3, 4, 5 times 10 to the minus 5, and then 2, 3, 4.5 times 10 to the minus 6, and all of that, you just keep going, whatever fits the issue. But the standard form would be that one. So I think, does anybody not understand that? I mean, am I not making sense? It's just a matter of putting it into a form that you want to use. Now, okay, multiplication and division. So I'll make up a number. Okay, I'll give you a second. So if you separate the coefficients and the exponents, you have something set up like this. And then times over here, you put all your exponents. And then work each one of those separately. We want to algebraically add these numerators, and you algebraically add the denominators because they're multiples. And then whatever you get out of these, you algebraically subtract the two. and that'll give you your power of 10 for that component of the calculation. Now, let's see what the coefficients calculator answer is. Let's see, so we get that from the separation of coefficients and exponents. If you want to jot that down. So I have this in the exponential category over here. So now I added the numerator, and of course I algebraically added the denominators, and I got that. So I'll subtract them this time. Minus 10 minus a plus 12, and so this ultimately works out to this 10 to the minus 22. Now then you want to put it in standard form, and for whatever reason we didn't, you want to round it to the least number of significant figures. Well, that of course is the 2 right there, so it'll be 3.8. Let's see, 5 goes to 2, so you want to get the 8 up, times 10 to the minus 22 is your final answer. Now, guys, I know I went fast through that. I'm not a math teacher. I'm a chemistry teacher. And so my object here is just to illustrate that. But we're going to be doing exponential notation so much as we go through the course. I think you'll get a handle on it as we go deeper. My suggestion is on this, be sure you're competent on your calculator with exponents. That's really where you need to be, because that's what I'll do. Yeah, if you move that decimal, you want to, of course, add another minus 1 in there because, thank you, dear. Okay. These are unit prefixes. You've heard of kilograms already, but what about nanograms, nanoseconds, and stuff like that? And it's a real simple. See, now you have to kind of sort of memorize these things, but I'll show you the relationships in here. And so, using prefix is an issue of applying powers of 10, just like we were looking at exponents. So, going above line is larger than the standard. So we have standards of meter, grams, and second. Now this is not the SI standard, obviously, but kilograms is. But I have to start with the basic, and that's the gram unit. And so what I'm going to do is come up here, times 10, times 100, times 1,000. These you will recognize as we. Times a million, times a billion, and times the terabyte size of 10 to the 12 up here. So when we talk about length in meters times 10, we call it a deca, and it's decameter, or decagram, or decatime. We're talking about blocks bigger than the standard. And if we're talking about 100s, it's hecto. So it's hectometer, or hectogram, or hectoseconds. And if we're talking about a hectometer, that's 100 meters, or 100 grams and 100 seconds. 1,000 is kilo as a prefix, and you know kilograms, so it's 1,000 grams. Kilometers, 1,000 meters, as a click, some people call it, and a time unit, kiloseconds. That's killing time? Okay. MEGA for a million units, megaseconds and megameters or megagrams. Giga, gig. If you're talking about a computer storage device, usually they're defined now in some of the larger ones in gigabytes. Now I've got a 5 terabyte system that went south on me, but it's this is what it means. So terameters, teragrams, teraseconds, or whatever the unit is, you hang that prefix on it. And if you're talking about bytes or quantities, that's a fundamental unit of computers storage. Now then you have, these are of course larger than the standard. And then smaller than standard. I'm going to need some more room over here, so I'm not going to put that in just yet. They need some. So this is 1/10, and that works out to be a 0.10 if you're doing a decimal, which is 10 to the minus 1 in a power of 10. Or 1/100th. 100, that's 0.01, which is 10 to the minus 2, and this one would be 1 over 1,000, and I'm going to name them in a second, and that's 0.001, that's 10 to the minus 3, and then you have 1 over a million. I'm not going to put that one, I'm just going to put 10 to the minus 6, and 1 over a billion. I keep wanting to put the negative in there. 1 over 9 and 1 over 12. So these are the ones that are primarily used. And this is deci. This is centi. This is milli, as we know it. This is micro, nano, and pico. So there are your prefixes that define fractions of the standard. 1/10 of a meter would be a decimeter, or 1/100th of a gram would be a centigram, or 1,000th of a second would be a millisecond. And so those are how those are simply applied, and they used to as a descriptive element of the dimensional size.